Hey, welcome back to Beard Squid. So in this video, I'm gonna show you how to verify and justify a quadratic sequence, a pattern, number pattern. We'll start off by using this particular pattern and then I'll go on to use another one. So stay tuned. Now, let's say, for example, the situation is that a tile company specializes in multicolored tiles and they generate this pattern. Now I like this pattern, but I want to figure out how many tiles of each color that I need for the nth term. So maybe I've got a space where, you know, I might need the 100th pattern or, you know, the 50th pattern. So I want to find out how many tiles I need for the nth pattern. Now, when I generate that formula, I want to know that it works, so I need to verify it. And I want to prove, I want to validate, okay, or justify how that pattern works, okay? So I want to look at the structure of the system and how it works. So this is a nice pattern. Let's start looking at this pattern. Before we move on with this pattern, let's do a few things. We can tabulate for this particular pattern how many greens, how many browns, how many yellow tiles that we need for each term, and then we can try to figure out what the total is and then generate a sequence or a general formula for that. So this is my first pattern or my first term, n equals 1, my second term, second pattern, and then n equals 3, n equals 4, and so on and so on and so on and so on. So I want to work out how many do I need for n equals, you know, the nth term, n equals 50, n equals 100. So let's have a look at this. This, I'll tell you off the bat, this is a quadratic sequence, okay? But there are constants in this sequence. There are square numbers in the sequence, and then there is a linear pattern as well. So let's have a look at this. So first thing first, I can see what I should do is maybe draw the next few to familiarize myself with the pattern. So I reckon if I draw the next pattern here, I might have 1, 2, 3, 4, 1, 2, 3, 1, 2. So I'm going to have 5 greens, okay? Now this isn't to scale, but I'll probably have 1, 2, 3, 4, 1, 2, 3, 4. That's my greens. And then I've got a layer of the browns, okay? Oh, that doesn't work, does it? I'm gonna have a layer of browns, like that. Just bear with me here. So they're my browns, and then I've got my yellows. So I'm just gonna label that yellow. Okay, they're my browns. If you're doing this in a test, maybe use colors, okay, or highlighters. That's not a brown, that's a green, okay? So that'll be my next sequence, my next pattern, the term, then I can do another. So that's a prediction that I'm making. I'm saying that the greens increase in length and width, the browns will follow the perimeter of the greens, and then the yellows are the corners, okay? So if I tabulate these results, then what we will have is we'll have n equals 1, okay, n equals 2, n equals 3, n equals 4, n equals, and I've got the fifth one there. I could do yellow tiles, okay, so yellow, 1, 2, 3, 4. For the first term, I've got 4 yellows. For the second term, 4 yellows. For the third term, 4 yellows. So what you notice here is that the yellow is constant, yeah? It's not changing. Then I can do browns, okay, so 1, 2, 3, 4 browns. And then 1, 2, 3, 4, 5, 6, 7, 8 browns. And if I carry on with this, I've got 12 browns, 16 browns, and then in my one here, I've got 20 browns, okay? I'll just confirm that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 browns, okay? And then I can do the greens. I've got 1 green, and then 4, and then 9, and then 16, and 25 greens. Okay, that's a 5 by 1, 2, 3, 4, 5. 1, 2, 3, I've messed up, haven't I? 1, 2, 3, 4. Oh, my browns. Look at that. See, this is the issue when you're not prepared to make a video. It's because I have to do this on the fly because I want to get it out there. So you've got some content that you can go over with my browns. You might be wondering, hey, when I made that shape, but the browns were at the end. So I got 25. So I got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's 25 greens. And now I can do a total as well, yeah? So total number of tiles. I'm going to call that T for tiles. And I've got 9 there. And then I've got here 12, 16. And here I've got 16 plus that, 25. And then here you can see I've got 16 plus 16, 32 plus 36. Okay. And then here, what do you notice here? Look, 9, 16, 25, 36. What do you reckon the next one's going to be? So I've got 45, 49. Yeah? Okay, so I've got my total number of tiles. Now what I can do is, at the end of it, I want to verify and justify that my general sequence, my general formula works for this particular pattern, okay? So what I'm going to do now is I'm going to take the total. I can take them individually. I'm going to take the total and I'm going to find out the first and the second difference in order to see if this is a linear or a quadratic or a cubic or whatever function it is. So let's take this here. Let's just rewrite it here. So I've got term n equals 1, 1, 2, 3, 4, and 5. And I've got my sequence 9, 16, 25, 36, and 49. 9, 16, 25, 36, and 49. Okay, and now I want to see what the differences are. So for my first difference, that's my T. This is going to be my first difference. Okay, so the first difference between 9 and 16 is 7. Okay, between 25 and 16 is 9. Okay, between 36 and 25 is 11. And then between 49 and 36 is 13. That's the first difference. Now my first difference is not constant, which means I need to find the second difference because I'm trying to chase the constant, okay? So my second difference, between 9 and 7, that's plus 2. Between 11 and 9, that's plus 2 again. And between 13 and 11, that's plus 2. So I notice now my second difference is constant. And because that's constant, I can now classify this as a quadratic sequence, okay? Now, because this is a quadratic sequence, there's a little shortcut that we can use in order to find out the general formula. Now, any quadratic or quadratic sequence would have the general form of an squared plus bn plus c. What we need to do is we need to try to figure out what the coefficients of n and the constant c is here. So we need to find out what a, b, and c are. And what we can do for that is use a key to unlock this combination. So we're going to be unlocking, we're going to use 9, 7, and 2, which is the first term of the sequence, the first term of the first difference, and the first term here of the second difference. Now the key that we're going to use, I'm going to have to erase some of this stuff, okay, so you can see what's going on. I'll take this off. And the key that we're going to use, this key that I'm referring to, I'm not going to explain where I get the key from right now because it's going to make the video extra long. But there is a video that I link in the description below where you can go and see how this works. Why am I using this key, okay? Where I generate this key from. So the key is A plus B plus C, 3A plus B, and then 2A. That's what I'm going to use to unlock this combination. And when I unlock the combination, I will get the values of A, B, and C, okay? So I'm going to use that to unlock. That's 9, that's 7, and that's 2, okay? So let's quickly find out what A, B, and C are. 2 times A equals 2, therefore A must be 1. Because 2 times 1 equals 2, so therefore A must be 1. Now that I have my A, I can substitute it into the second equation to find out what B is. So let's substitute that. If A is equal to 1, 3 times 1 is 3. 3 plus something, 3 plus B equals 7, so therefore B must be 4, okay? So I have my A, I have my B. If I substitute it into here, I can find out what the value of C is. So A is 1, B is 4, that's 5. 5 plus C equals to 9. So therefore C is, was it 5 or 4? It's 4. Okay, so that's my A, B, and C. So for me to write this, the general quadratic sequence, the general formula for this particular pattern, for the total number of tiles, is going to be, instead of an squared, I'm going to write 1. Okay, so 1n squared. And now, since it's 1n squared, I don't even need that 1, so I can just get rid of that 1. And then B is 4, so I can take that B off and write there 4. And my C is also 4, and that's my formula for the nth term of this sequence. Now, since I'm looking for the number of tiles, this is the total number of tiles for this particular sequence. This is a total number of tiles. I said at a point that I want to find out, in the beginning of the video, I said I want to find out for the nth term how many greens, how many browns, and how many yellows I wanted, okay? So that's I'm gonna use that information. I'm going to generate information for that to actually justify how this particular formula works. Now, before we do that, let's verify that this works. And an easy way that you can verify it is use one of the terms that you already have to see if you can generate that number of tiles using this formula, okay? So, for example, we know that we've got term 1, 2, 3, and 4. So I'm just going to substitute n equals 4 into this formula to see if we get a total number of 49 tiles, okay? Because this is 1, 2, 3, 4, 5. Oh, that's a fifth one, sorry. 36 tiles. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 6 by 6, 36. So we're looking for 36 tiles, okay? Using this formula for n equals 4. I'm verifying. So let me just, you see, I need to find space on my board now. I don't necessarily want to erase this. Let's just substitute it somewhere, okay? Oh, for God's sake, I'm going to have to erase. Let's go on to another board. Actually, we'll just migrate to another board. Okay, let me see if this is set up well. I think this is good enough. So what I'm waiting to do is I had un is equal to n squared plus 4n plus 4. That was my general formula, the general formula for this particular pattern. Now, I'm waiting to substitute when n equals 4, I know that I have 36 tiles. So I want to make sure that when I substitute n equals 4 here, I have the value of 36. So let's substitute it. I've got 4 squared plus 4 times 4 plus the 4. 4 squared 16. 4 times 4 is 16. And plus the 4. 16 plus 4, that's 20, that's 36. Okay, so here U4, when I substitute the value 4, I get 36 tiles. Now, pay particular attention to these numbers here. We've got 16, 16, and 4. Now, this was when n equals 4. This was the fourth pattern. This was the fourth pattern in that sequence. 16, 16, and 4. What is 16 and 16 and 4? Now, this is going to work towards justifying the actual formula, okay? What does justify mean? Well, if I show you the command wall over there, I'll point towards it. Justify, give a valid reason or evidence as to why the system works, okay? What the structure of the formula, I need to provide evidence or reasoning as to why it works. Now, let's take it back to this board here. Okay, I had 16, 16, and 4. Well, what does that 16, 16, and 4 refer to? If I come over here and I show you the fourth pattern, where am I showing you? Okay, here, the fourth pattern. Here, this was n equals 4, okay, when n equals to 4, I had 16, 16 green, 16 brown, and 4 yellows, yeah? That's what it refers to. So I now need to justify this formula by breaking down the structure, okay, the structure of the formula. So this is how I would possibly justify this, this problem here, is I would go back and refer to this table, okay, and show you. Let me get some space here now. Maybe we show you here. Okay, so in terms of justifying this formula here, the general term, I have verified using n equals 4. I could also verify one step further by observing the pattern and taking outside the range of the table. So I remember in the sequence I had 1, 2, 3 and 4 terms, or the patterns 1, 2, 3 and 4, and I predicted the fifth pattern, isn't it? Yeah. If you recall, I did erase it on the board. The fifth pattern had 49. The fifth pattern had 49, that was n equals 5, and it had 49 tiles. Now, in order to continue this verification, I could therefore say, okay, I don't know if this is getting the whole formula. Let me just angle this up, one sec. Okay, so this is my verification, okay? Verify. I could further verify this by using a term that's outside of my sequence, so the fifth term, for example. Now I know the fifth term is going to be 49 because I've proven that in the table already by using my prediction. So I could therefore go ahead and just say, hey, when n equals 5, I should have 49 tiles, and refer back to the sketch that I did for the fifth pattern. And if I do substitute this into here, 5 squared plus 4 times 5 plus 4. Can you see that on the camera? Nope. So let's make that adjustment again. What I can do, just put this back a little bit. Okay, so that would be 25 plus 20 plus 4. 25, 20 plus 4, that makes 49. And if you go back to the table, the original table that we had, you can see remotely that we had, shall I bring it? Here we go, look. You can see that we had, for the fifth pattern, when n was equal to 5, we had 25 greens, we had 20, so 25 greens, we had 20 browns, and we had 4 yellows. So that is proving the structure of this sequence. And in fact, what I'm going to show you now is this. Look, the pattern always has a constant 4 yellow. Okay, we constantly have 4 yellow tiles on the corners. That is, let me get rid of this, I'll just show you here. So the formula that we have, un is equal to n squared plus 4n plus 4. I'm going to now justify this, okay? We'll justify by looking at each component separately, okay? So we can justify that the whole formula works together. So this 4, the plus 4, what does it refer to? Well, the plus 4 refers to the yellow tiles on the corners. So since each pattern has 4 yellow tiles at the corners, we always have a constant plus 4. Okay, that's proving this part of the formula using the shaded. We can, if you know, if you're in the test and you're doing this, make sure you color code it so you're proving each part of the structure of the system, which is since each pattern has 4 yellow tiles at the corners, we always have a constant plus 4, okay? That's important. We have a constant plus 4. Now we can do the same thing for the plus 4n. Where does the plus 4n come from? The plus 4n comes from this linear sequence here, the brown tiles. So if we go back and we look at the brown tiles, okay, pause the video here and copy this down because I'm going to erase it. I'm running out of space here. Okay, I'm going to erase this. So that's the plus 4 for the yellows. So we're justifying each part of this formula, and we're saying that this constant here is because we have the corners, the four corners, the yellow tiles, which is a constant of plus 4. Okay. Now I'm just going to erase it because I ain't got space for this. I'm going to now go and justify the 4n. Okay. So pause if you must and copy this down. I'm taking it away. Okay. So now we'll justify very quickly the 4n. Where does the 4n come from? So now if we're looking at the brown tiles, okay, the brown tiles actually represent the perimeter of the green tiles, okay? But if we look at the brown tiles, we've got for n equals 1, 2, 3, 4, we've got 4, and then 8, and then 12, and 16. Now what you notice about these, they're just multiples of 4, yeah? And if we go ahead and we find out the first difference, plus 4, plus 4, plus 4, this is a linear sequence. This is a linear sequence that follows an plus b. There's no squared term here, just an plus b. We're going to find out what this linear formula, the linear general term for this linear formula here for the brown tiles. So since the constant difference here, the second difference, the consecutive difference is 4, we have A is equal to 4n, that's our consecutive difference, and then B is our adjustment layer. For example, if I do 4 times 1, when n equals 1, 4 times 1 is equal to 4, 4 times 2 is equal to 8, 4 times 3 is equal to 12, and then 4 times 4 is equal to 16. So we don't need to add anything for B. B is going to be 0. If we substitute, if we're looking for n equals 1, and we substitute here 4 times 1. 4 times 1 is 4. So that's perfect, that's correct. If I done for u2, that would be 4 times 2. 4 times 2 is 8. So that's perfect. So there's no adjustment here. For the brown tiles, we have the formula 4n. Now, that satisfies, okay, where we get the 4n from. So since the brown tiles in each pattern follows a linear sequence, which is an plus b, the formula for that is 4n, since we have a consecutive difference of plus 4 each time. So that justifies and proves this component, this part of the structure of our quadratic sequence. Now we need to prove where the n squared comes from, okay? The n squared. So pause if you must, copy this down, and then I'm going to go ahead and prove or justify where the n squared comes from, okay? Rightio, so we're looking at n squared. Where does n squared come from? So we're looking at the green tiles, okay? And what the green tiles actually represent, you've got for n equals 1, 2, 3, 4, and so on, we've got 1 green, then 4, then 9, and then 16, okay? So what we have here is we actually have square numbers. If you look carefully, that's 1 squared, which is 1, 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16. And if you refer back to this diagram, you can see that the green, 1 by 1 is 1, 2 by 2 is 4, 3 by 3 is 9, and a 4 by 4 is 16. These are square numbers, okay? These are square numbers. Now we could go ahead and actually, using the key that we did before, find that this is a quadratic sequence. But I think that you are pretty familiar with square numbers, and the fact that the sequence for square numbers would just be n squared, okay, n squared. And we can see that that works because when n equals 1, 1 squared gives you 1, 2 squared gives you 4, 3 squared gives you 9, and 4 squared gives you 16. So that's the part that justifies here that we have a set of tiles within our sequence that gives us the square number, okay, n squared. So if I did want to find out for n equals 50 or n equals 100 or n equals 200 or whatever, each part of this actually refers to the green tiles, the brown tiles, and the yellow tiles. So I could really quickly find out by substituting any value of n into my quadratic sequence, the formula, to find out how many green, brown, or yellow tiles that I may need. So this is your justification before we've done the verification, and that's basically the end of the video. What I will do is I'll try to do another one, but instead of using square numbers, a constant, and a linear pattern here, I will use triangular numbers, okay? And that's quite useful for a lot of different number patterns, okay? So I'll link to the video which is explaining where we get the key from and other quadratic sequences, okay? As well as possibly another video that I'm going to make using triangular numbers, okay? As always, I hope you enjoyed that. If you've got any questions, put them in the comment below and consider subscribing, and I see you in the next one.